Okay, back page. Here are the steps for finding absolute extrema of a function. Okay, again, this is analytically, right? So if you can just graph it, then that's fine. But if it's a non-calculated part of the AP test, then you got to think about how to do this stuff analytically. All right, so first step is take the derivative and find the critical points. Then you're going to evaluate the function at the critical points and the endpoints. Okay, so critical points will help us figure it out on if the domain is all real numbers. But if there's endpoints, so if it's on an interval, then we'll need to check those as well. So in short, absolute extrema can only occur at critical points or at endpoints. Okay. Also, it should be noted that all extrema are critical points. Not all critical points are extrema. Okay, so this is an important thing to highlight. All right, so number 5 here, example number 5. We're going to find the derivative first. So f prime of x to the 2/3 is going to be 2/3 x to the negative 1/3. And then I am going to write this in root notation just so it's a little bit easier to analyze. So this ends up being 2 over 3 times the cubed root of x. All right, so we're going to search for critical points. Critical points occur whenever the derivative is 0 or fails to exist. It is never 0, but it does fail to exist at 0. So one critical point is at x equals 0. Okay, so now we're going to analyze the function now to figure out if 0 is an absolute extrema or not, or whether it's an extrema or not. Okay, so I'm going to figure out f of 0. And when I plug in 0 to the original function, I get 0. I'm going to take f of negative 2, and when I plug in negative 2 to the original function, I'm going to get 1.6. Again, I'm checking negative 2 because that is an endpoint. I'm going to check the other endpoint now, which is 3. When I plug that in, I'm going to get that f of 3 is equal to 2.1. Okay, and I'm checking the original function here because I'm trying to figure out where the highest and lowest points are on the interval, of the function on the interval. Okay, so of the actual function. So I check f of 0, I get 0, 1.6 at negative 2, and 2.1 at 3. That means that there's a minimum at 0, an absolute minimum, at 0, 0, and then an absolute max at 3, comma 2.1. How do I know that on the interval that there's no other places that could be higher or lower than those points? Well, there's no other place for them to hide. It's either got to be at a max or a min, which would show up as a critical point, or it's got to be at an end point. So that's why you check the endpoints and the critical points, right? So there's no place else that it could hide. All right, let's do one that's slightly more interesting to analyze. Let's find the extreme values of this function here in number 6, 1 over the square root of 4 minus x squared. Okay, so the first thing I'm going to do is I'm going to rewrite this in rational exponent form. So it's 4 minus x squared to the negative 1/2. And then I'm going to take the derivative. So f prime of x is going to be negative 1/2. Leave the inside alone. Subtract 1 from the power. Times by the derivative of the inside. It's negative 2x. Here we don't necessarily, I guess, have to simplify, but it's certainly in our interest because we're trying to do this analytically and we are not going to be using a calculator. So we need to, so it's probably going to be helpful to have this in the nicest form, the most simplified form. I have a negative times a negative, that's a positive. 2 times 1/2, that's 1. So this is all going to multiply to be positive 1. I'll have an x in the numerator and a square root of 4 minus x squared in the denominator. So ultimately, it will all look like this. X divided by the square root. I should have left more space for this. 4 minus x squared. I had the space. Cubed. Okay. Now we're going to do some analysis. When is this thing equal to 0? Well, let's check. Set it equal to 0 and solve. Okay, a fraction a rational expression with an x in it is going to be 0 whenever the numerator is 0. So we want to know, when is x equal to 0? Oh, hey, x is equal to 0 when x is equal to 0. Okay, so there's one critical point at 0. We also want to figure out when the denominator is 0, because that will also be where the derivative doesn't exist, right? It will. The critical points are when the derivative is equal to 0, or when it fails to exist. This will fail to exist when the denominator is 0. So let's check. When is the square root of 4 minus x squared cubed equal to 0? Okay, well, I'll square both sides, and then I'll also cube root both sides, and I think I'll get this. 4 minus x squared equals 0. And so that will be equal to 0 whenever x is equal to positive 2 or negative 2. So there are my 3 critical points. And again, not again, but I'm looking at the entire domain of this function. I'm not restricted to endpoints. So here are all the places where I could have an absolute extrema or a relative extrema at negative 2, 0, or 2. I'm going to put all of these on a sign chart and do some analysis. So I'll put negative 2 here, I'll put 0 there, and 2 there. Okay. So let's pick some values, and here we're checking the derivative because we want to know, when is the derivative positive or negative. That will tell us increasing or decreasing on the original. It'll tell us maximums or minimums. So if I plug in negative 3 into the derivative, did I write this out? No, I didn't. I don't think it exists here. So here I'll have 4 minus 9. That's negative 5. Negative 5 cubed is a negative number. Square root of a negative number is impossible, so the derivative doesn't exist over here. Same thing is going to happen if I plug in positive 3. 4 minus 9 is negative cubed, which is negative. Square root of a negative is impossible, so it doesn't exist over here. So I'm only looking between negative 2 and 2, which, by the way, makes sense because the domain is only from negative 2 to 2. Okay, so let's check between 0 and negative 2. I'll just pick negative 1. It's a nice, easy number to compute. So I get 4 minus a negative 1 squared, which is positive 1. Actually, you know what? I'm doing this. I don't actually need to plug that in, right? Because the square root on the denominator is always going to be positive so long as it exists. So if I plug a negative 1 into the top, I'll have negative 1 over a positive number, which means this has to be negative right here. And if I plug in positive 1, I'll have positive 1 over a positive number, which means it's got to be positive right here. Okay? So that tells me that I must have an absolute min at the point 0, comma, and when you plug in 0 up here, you'll get 1/2. So 0, 1/2. Okay? Again, how do you know it's not any other place, Mr. Cresswell? Well, that's because there's no place for an extreme value or a minimum or a maximum to hide. It's either got to be at a critical point or an endpoint. There are no endpoints in this situation. So it has to be at 0. And you can confirm this graphically too. If you graph 1 over, maybe we'll do it, I guess. It's already been a super long video as it is, so what's another minute? 1 divided by the square root of 4 minus x squared. The graph on that. And there's your graph. There's actually vertical asymptotes there going up. That gets cut off by the 83 plus here. But there is a minimum at 0, so we can confirm it graphically. All right, that's it for section 5.1. Like I said, recapitulation of a lot of stuff that you're probably aware of, but we're trying to formalize it here and trying to take a much more analytical approach to this using the tools that we learned in chapters 3 and 4 to nail down mins and maxes, increasing and decreasing ultimately too, without using a calculator. And I think that's pretty much it for 5.1.